Hi, I'm Aditya, and I'll be demonstrating my first lab assignment for the course EE542, which is a client and server model using sockets in an emulated network on virtual machines. So the first thing is to set up our Linux on VirtualBox. So I'm using three virtual machines, which are basically a linked clones for the base virtual machine that's running Ubuntu. So I'm renaming them as PC1, PC2, and router. The network topology that I'm using for the first case, that is network using a Quagga router, is that PC1, router, PC2, all are virtual machines, creating an internal network between PC1 and router, internal network between router and PC2, and assigning them static IP addresses for the interfaces on PC1, router, and PC2, as well as on the network. So this everything is inside VirtualBox, which is running on my real computer. So these are the prerequisite network adapter settings that need to be done. For PC1, PC2 router, we'll have additional adapters so that they're internally connected. So this forms a point-to-point connection. And then we assign port forwarding rules for PC1, PC2, and router because so that I could remotely access these machines via SSH using these ports. So going over the demo for the Quagga router. So as you can see, I'm running all the three machines, and the actual windows are in my different monitor, and I'll be using SSH to remotely access these machines. So these machines are created using the memory settings and network settings that I described in my previous slides. So router will have Internet A, Internet B, and NAT. PC1 will have NAT and Internet A, and PC2 will have NAT and Internet B. Great. As you can see, I've used the corresponding port to access my corresponding machine. Right, PC1, PC2, and router. So as you can see, I've statically assigned 192.168.1.1 this interface, which signifies my internal network, and similarly for PC2. And since router has two interfaces, it will have two static IP addresses assigned. So I formed a route from PC1 to router, and then router to PC2 as well. Right. So now I'm pinging my PC2 from my PC1, and as you can see that I'm able to transmit my packet successfully. Same way, I'm pinging my PC1 from PC2, and as you can see that I'm able to send packets across the network. So I'm using another command called traceroute, which gives me the number of hops that it's away from the destination, right? So as per our network topology, and as you can see on the result that both are 2 hops away from each other, with the middle node being the Quagga router, right? So these are the screenshots for the demo that I just showed you. So this is for PC1, the commands that I use: traceroute, ipname, iproute, ping, and the same for router and PC2. So why are we using YOS? So Quagga does not have a support for DHCP, so that's why we are statically assigning IP addresses on a Quagga-based router-centric network. So YOS has support for DHCP, and YOS is a 64-bit Debian-based open source router. So we need to create a separate VM to run YOS. So there's a slight change in the network topology. Instead of assigning static IP addresses to PC1 and PC2, that responsibility is given to the router because the DHCP server running on the router will assign the IP address for the clients that it's connected to, right? So we specify the network. Internet A will have the IP address of this. Similarly for Internet B, and I'm assigning IP address for ETH1 and ETH2, these IP addresses. And as same as before, these are all connected to my virtual box on my real computer. Again, these are the prerequisite network adapter settings that need to be done. So this is exactly the same as before to form the point-to-point connections. The only difference being that the port forwarding rules won't be applied for router because it's connected via bridged adapter. So PC1 and PC2, I'll be able to access them remotely via SSH using these ports, but for router, I'll be using the actual VirtualBox window. Going over the YOS demo. Same as before, all three are running. with the same network settings and memory settings. And as you can see, that I'm accessed my PC1 and PC2 via SSH, but I'm actually running my router on the actual VirtualBox window. So these are the configuration settings for my router. So ETH0 signifies the bridge adapter, and its address is assigned by DHCP because it's basically connected to the outside world. ETH1, I have assigned the static IP address for this, ETH2 address for this, and I'm describing as Internet A and Internet B for this particular interfaces. So for DHCP server, there are two shared network so that the clients from for different networks can be assigned an IP address by this particular DHCP server, right? So the default router for Internet A would be the same as ETH1, default router for Internet B same as ETH2, and basically these are the range of IP addresses within which the client will be assigned an IP address. Similarly for Internet B, right? Now, show interfaces command will give me the basically concise view of all the interfaces, their IP addresses, and their description. So as you can see, this IP address has been assigned by the outside world, while these two I assigned it specifically and described it as Internet A and Internet B. Now, as you can see, PC1 has been assigned 192.168.10.10 and PC2 has been assigned 192.168.11.10 by the DHCP server. Right. So basically to check that, we see on PC1 that it has been assigned the specified IP address for this particular interface, and similarly for PC2 as well. Right. Now, same way before, like I'll ping my PC2 from PC1 and I'm able to send packets across. Doing the same thing the other way around, pinging PC1 from PC2, and as you can see, then I'm able to send packets across. Running the same trace route command to check how many hops away is my destination, and it should be the same, that is 2, and that's what's been expected as it can be displayed on the screen. Right. So these are the screenshots for the demo video that I took. So this shows my configuration settings for the router, the DHCP server, the assigned IP addresses for the clients, that is PC1 and PC2, and basically doing the check whether the connection has been established, same way as before. Now we jump to the last topic, that is client and server socket programming. So essentially, we would want PC1 to be acting as a client and PC2 acting as a server. So client side will have these steps, basically create a socket, connect the socket to the address of the server, and send and receive data. The server side will have first to create a socket, then bind the socket to the server's address, listen for connections on the socket, and we accept a connection. And first, we wait until the client connects to the server and then accept a connection. After accepting the connection, we send and receive data accordingly. Now, a real world server would have the ability to handle multiple simultaneous connections and it'll run forever, right? So for that, we use an infinite loop so that it never dies. And we'll be using the fork system call to create different processes as and when we get a new connection, right? So the child process, which signifies a new connection, will exit after completing the conversation. So after exchanging data from client to server, server to client, it'll exit. And the parent process will return to the accept statement to wait for new connections. Now, this entails a problem called zombie problem, which is nothing but accumulation of zombie processes on the kernel process table. A zombie process is a child process that is supposedly dead, but not completely dead because the parent process can invoke a system called wait to get the details of the death of the child. So to avoid this problem, there are many ways. So one of the ways that I incorporated on my uh, programming code is that we ignore the signal that is sent by the child process after it dies. So there is no entry in the kernel process table. Another way is to explicitly make the wait system call as soon as we get the signal. So I implemented the first method because it's fewer lines of code. right? So before I show the demo, I just want to go in depth on the code. So this is the TCP server, and as I mentioned in my previous slide, the server steps we would have first to create a socket. So that's how we create a socket. We specify the internet domain. Sock stream and 0 would specify that it's a TCP protocol, right? And then you bind the socket to an address. We bind the socket, which is here. We bind the socket to the uh, address of the machine that's running the server code, which in our case would be PC2. And then we listen for connections on the socket. This is the listen system call. And then we wait until uh, a client connects, right? So the accept system call blocks the flow of the code. And as soon as a client connects, it basically goes ahead on the process, right? So as you can see here, the accept would return a socket file descriptor, which would we be referring to specify that we're listening and we are accessing this particular socket, right? And as soon as we pass this line of code, we invoke the fork system call, which would create a separate process for each connection, right? If it returns a negative value, that means there's some error on fork. If it's zero, then that means it's returned to the newly created process, right? So we go ahead and basically do stuff function would essentially mean that we are exchanging data from client and server. So read system call basically read from the socket, and write system call basically write to the socket. So that's how we are exchanging data through the sockets, right? So if it's not zero and if it's not negative, that means it's positive, right? So positive means that it's returned to the parent process. And when we are in the parent section, we would want to ignore the signal that is sent by the child process after it dies, right? So that's how we are avoiding the zombie problem. And then we basically loop back to the accept statement and wait for a new connection, right? And similarly for client TCP, uh, the steps are to create a socket, connect the socket to the address of the server, and then send and receive data, right? So we first create a socket using the socket system call, same way, internet domain, and sock stream 0 means TCP, right? One thing that I forgot to mention is that we would create an error message if the arguments for the client side is less than 3. That is because we would need the user to pass the IP address of the server as well as the port number that the server is connected to. Same way for server, we would want the user to pass the port number as our argument, else it would basically result in a error case, right? So circling back to where we left off. So after creating the socket, we basically get the details of the server's address and then connect to the socket and write and read accordingly, right? So jumping for UDP, you can see that there's just a small difference is that we don't have, for the server's case, we don't have basically listen and accept system call. We have receive from and send to. There's no handshaking in UDP, right? So first, we create a socket by specifying that we are using a datagram instead of a string, and this would signify that we are using UDP. And then we bind the socket, and since there is no handshaking, we would want every time that the signal is being ignored, so that there is no uh, accumulation of the zombie processes whenever uh, client request is done and the client process is dead, right? So we use receive from and send to instead of read and write for communicating data between client and server. Similarly for client, instead of read and write, we would use send to and receive from, same way, and create the socket the same way as server, right? And yeah, so that's how UDP is done. And another way is the previous two were on the internet domain where we use the IP address of the server and the port number, right? Now there's one more we call Unix domain, which is basically exchanging data, basically client and server model on system that shares the common file system, right? So within the same virtual machine, essentially. So in my demo that I'll be showing in a minute, I'll be doing that on PC2. So my client and server would run essentially on PC2, right? So instead of AFINet, the previous, while we create a socket, we just specify that it's Unix domain. And same way as before, we just read and write to exchange data. So this is for client. Similarly for server, we just use EF Unix and then read and write. Listen, bind, all the steps are same for server. Right. Now jumping to the demo. So as you can see, I have three windows for PC1 open and two windows for PC2 open. And as you can see, by default, there are no zombie processes. So first, I'll be running the TCP server code running on port 555, and I'll be specifying the IP address of the server and the port. And as you can see, I'm able to handle simultaneous client requests on the server side. And as and when a client ends its communication with the server, it exits out of the code, and there are no zombie processes being accumulated because of the signal ignore code line of code that we implemented. Now doing the same for UDP, same way, I'm able to handle multiple connections simultaneously and avoiding the zombie problem because there is no accumulation of zombie processor. So now you can see that I'm getting extra characters here. That's because I'm using UDP. So it's not as reliable as TCP, but it's faster than TCP because there's no handshaking, right? So now I'll be showing the Unix domain case, and instead of the port number, I would be specifying the path name as my argument. And similarly on the client side, since on the same file system, I wouldn't need IP address because that's for internet domain. But now we are running the Unix domain, and we'll be specifying the path name. And as you can see, that as and when I write and read data, the communication is sent across, and I'm getting the data as expected. Right. So this is a screenshot of the previous demo video that I just showed, and that concludes my demonstration. Thank you.